guys, my name is Abhishek Bharadwaj and I am 17BEE0027. I'm a student. So guys, today we'll be talking about electromagnetic wave propagation, that is EMP, has been mentioned over here. In this topic we are going to talk that how we can use Maxwell equations in brief to prove the electromagnetic wave propagations and the equations which are involved. Basically some of the equations which Einstein and the other scientists proved, like c square is equals to 1 over mu naught epsilon naught, and some related equations which we can prove actually using electromagnetic wave functions and in form of Maxwell equations. So let's start. So guys, first of all I would like to tell you about the Maxwell equations which all we took into account. But before that, we would like to talk on the main topic, which is that displacement current. Actually, before getting into the account, the scientist Maxwell, he gave this term as displacement current. Why did he introduce this thing? The main reason of introduction of the displacement current was that suppose this is a capacitor, it's having a charge. With the more accumulation of the charge on one side of the capacitors, the more will be the electric field will be coming out as more and more. So due to the electric field, we can say that if electric field is there, then it is directly proportional to that of the charge, and if the charge is there, so flow will be also there, of course, and because of that, yeah, electricity will be there. So as usual, there is some current, suppose it is going inside the circuit, and there is some other current will be generated in this part of the particular circuit that he mentioned as the ID, and which further we know that it is equals to mu naught epsilon naught d phi E by dt. So this is what he proved. So now basically why do we use it? Because since this part of this thing will be not there, so it will violate the conservation laws and other stuff. So yeah, to prove this thing, the flow of current between the capacitors, displacement current was taken into account, and therefore we were out with some of very good equations which nowadays we use. So these equations goes on like this in integral form. In integral form, we write these equations like this, and we also have one other form of equations, that is the differential equations form. So we're going to discuss both of them. So first one is the integral. We can say that the double integral or the surface integral of that of electric field with the area as it is the surface thing will be nothing more than that of q by epsilon naught. Also, we can say that the line integral of, or actually surface integral itself, E dot ds will be equals to minus d phi b, that is the flux due to the magnetic field originating with respect to time if we differentiate. The third equation we come out is double integration or the double surface area integration of b dot dA is equals to 0. Now why this thing is to be 0? Just because we are not able to find a monopole thing, so yeah, it's not there, so this can be set 0. And the fourth equation, that is the surface integral of a magnetic field, B dot ds will be written as mu naught I plus mu naught epsilon naught d phi E by dt. This thing is being the displacement current part. So these are all the integral forms. We won't use them, but we will use the displacement, the differential equation form of these equation to prove our stuffs. Let's go on to the differential equations. Differential equations are written as del, which is known as the divergence. So we can use that del dot E is equals to rho by epsilon naught. Second equation, del cross E, that is equals to minus dB by dt. Third equation, which is say del dot B is equals to 0, as no charges there. So, and the fourth one is del cross B, that is equals to mu naught J, which is the current density, plus mu naught epsilon naught d E by dt. So these are the all four equations in brief, which Maxwell and the other scientists used to make approval of that electromagnetic field, and they gave it as a function, which is the generalized form of that second order function, out of which they gave out the equations, and later they were able to solve that how C is equals to inverse of 1 by mu naught epsilon naught, and in general epsilon m and that mu n, which depends on the medium.
A few moments later.
Proving the electromagnetic wave equation using our Maxwell equations, which we already wrote earlier. So now I'm going to prove it. So in general, we start with our equation prover. So we say that the application of Maxwell equation is the prediction of existence of electromagnetic waves. So that's what the basic idea behind which this whole thing is working. And according to that, we use the Maxwell equation for the Faraday's law, which was the first equation that we can give as this thing, del cross E. That is equals to two forms. We have red minus dB by dt and the other form. So we'll go ahead with by the first form of the equation, that will be minus dB by dt, and so which can be actually written as minus mu times of dH by dt, and we know that the H over here is the magnetic field intensity which we have taken over here. So H, for clearing the doubts, it's magnetic field intensity. Okay, so now after that, this, as we know, if we all have studied, that this cross is actually, can also be said the curl of this thing. So taking the curl of electric field, we got this as our equation. So now taking a double curl of this thing, that means the curl of curling electric field, we can say the equation will come out like this, into my mu, into that is the curl or the cross product, we say in general, dH by dt. So it can be further written as del cross H is equals to J plus may dB by dt, where J is the current density as told earlier, and dB by dt, you all know what we are talking about here. So this is the first thing which came out due to the Ampere's law, and which was generalized and can be written as sigma times of E plus may epsilon times of dE by dt. Now after this, if we differentiate this equation with respect to time, we get that del cross dH by dt is equals to dV cross H by dt. V cross H, since the cross product has been taken inside, so I can say that this thing has our main thing. And now we continue on this. So hereafter we can write that d by dt taking as a common outside, sigma times of E plus may epsilon times of dE by dt. And this can be further written as del cross dH by dt is equals to sigma times of dE by dt plus may epsilon times of d square E by dt square. This, since this was the second differentiation after the first thing, if we differentiate it this way. So after that, we get the equation as per we wrote this thing, del cross dH by dt on the other side. So taking these all factors on the other hand side, or just letting it to be in the journal form, we can write it as this, del cross dH by dt is equals to sigma times of dE by dt plus may epsilon times of d square E by dt square. So which we can now equate from the earlier equation which we read, the curl of curling electric field, that is del cross E, that is nothing but it will be equal to minus mu times of sigma dE by dt minus mu E d square E by dt square. As comparing the two equations, we get this as our final equation. And now operating del cross, that is curl of curling electrical field, we can solve the remaining part. And so on operating it, we know that we'll get del cross E is nothing but del dot E minus may del square E. So using this form of equation, we write it as del dot E is equals to 1 by epsilon times of del dot D, and del dot D, since the charge is not there, will be 0, and del dot E similarly will be 0. So we can write this thing as in a journal form like this, that del cross E will be nothing but minus del square E. So after this, putting this as in the first equation which we solved, that was the earlier equation just time before I solved. If we find out the left hand side and the right hand side and substitute the values, we get this equation as follows: del square E minus mu sigma minus mu epsilon d square E by dt square, where sorry, this thing was missing here, dE by dt, and this whole equation will be 0.
A lot of boring math later.
From here, if we compare this as the second order differential equation, so we get this thing that C will be inverse of 1 mu epsilon under root, basically, sorry, C square will be equal to this thing. And now taking roots on both sides, we can write as mu naught epsilon naught. And we also know that this factor can only come with the ratio of E naught to B naught. So we can also write it in the form of E naught by B naught is equals to C. So this is just one of the basics thing which we can do with the help of divergence and curls and with the help of our Maxwell equations and other stuff. There are many other things which we can prove using these equations. If we go into ours, the topic is very large. So with this, I would like to conclude my topic.